Consumers experience AI as a reactive interface, but enterprise finance is migrating to Agentic AI, designed to operate autonomously, executing commands without a human pressing enter. The industry is handing the steering wheel of the global economy over to these self-executing networks. Giving an AI the agency to trade billions of dollars introduces an immediate vulnerability. Neural networks are notoriously prone to hallucination. They excel at finding patterns that simply do not exist in the physical world. When an AI autonomously ingests unstructured real-world data, analyzing the sentiment of geopolitical news feeds or tracking satellite imagery of oil reserves, it can formulate a mathematically flawed assumption based entirely on the subjective vibes of a market. We already know the physical stakes of mathematical failure. In 2008, models designed to measure risk failed to spot the cliff, and trillions of dollars vanished overnight. To survive the integration of agentic AI, infrastructure must fuse the unpredictable intuition of deep learning along with the rigid, unbreakable limits of traditional stochastic calculus. Scaling machine intelligence is only viable if it is coupled with an absolute, fail-proof mathematical leash to contain it. Following the 2008 collapse, global regulators established Basel III, demanding that banks hold massive capital reservoirs to physically prevent bankruptcy during severe market panic. This presented a massive engineering problem. A bank cannot calculate a survival reservoir based on average daily metrics. They have to calculate precise financial exposure against multiple, compounding global disasters occurring at the exact same time. The mathematical solution enforced to solve this is a framework known as the Fundamental Review of the Trading Book, or FRTB-SA. You cannot process multivariable exposure with basic algebra. Quants rely on Monte Carlo simulations, determining a bank's survival probability by playing out alternate realities. They mathematically compress millions of variables into a definitive capital requirement limit. These exact multiverse calculations are built into every level of vulnerability. For example, interest rate risk in the banking book, or IRRBB, uses this probabilistic math to insulate legacy loans from sudden central bank rate spikes. Writing the C++ and Python code to run these massive stochastic shock absorbers consumed the better part of a decade for top-tier Wall Street quants like Ratanlal Mahanta. These statistical frameworks provide the structural stability that keeps global markets from collapsing under their own weight. They provide the verifiable proof that an institution can physically survive a panic. Historically, quantitative finance operated on the doctrine of algorithmic alpha. Firms treated their mathematical models as proprietary secrets, locked tightly in closed-source codebases. This secrecy created an extreme opacity crisis. Banks assured regulators their algorithms were safe, but outside analysts lacked the ability to read or verify the math. Mahanta directly countered this culture, publishing over 15 open-source technical cookbooks. These books explicitly detailed how to build complex risk frameworks using standardized Python and R programming. Standardizing the underlying plumbing gave the broader quantitative community a shared baseline. It allowed peers and regulators a unified language to rip apart, analyze, and mathematically verify any bank's risk claims. This aligned the industry with the academic principle of reproducible research, treating quantitative finance with the rigid transparency of a hard science. But solving the opacity crisis triggered a massive unintended consequence. When the industry adopted open-source math, it removed the friction of translating models between different firms. This streamlined pipeline allowed data to surge through the global market at a volume and speed that no human team could ever reconcile manually. Because computers could now communicate in a perfectly standardized language, market events began moving in millisecond intervals. By removing the friction of human translation, quants inadvertently made human oversight a physical impossibility, leaving AI as the only system fast enough to manage the surge. An agentic AI digests a terrifying scope of variables. In a fraction of a second, it can ingest the emotional tone of a CEO's tweet, analyze global shipping logs, and assess the physical supply chain logistics of a cargo fleet. Deploying pure neural networks to evaluate this data introduces an epistemological vulnerability Mahanta defined as making facts by design, where models wield too much authority. The mechanics are straightforward. If an autonomous AI hallucinates a minor vulnerability and lowers a business's credit score, the bank inherently trusts that model and denies the business a loan. Because capital was denied, the business cannot expand, their revenue drops, and they genuinely default on their obligations. The AI did not predict the default. Its autonomous action dictated reality. Scaling this localized effect globally triggers endogenous liquidity amplification. One AI system overreacts to a minor market dip. Competing AIs instantly detect that action, assume a hidden danger exists, and trigger massive sell-offs to protect their portfolios. In minutes, liquidity dries up completely. The terrifying reality is that this massive market drain is generated entirely from within the automated ecosystem itself, without a single real-world economic trigger occurring. When hyper-fast autonomous models rule the market, the models themselves become the greatest hidden systemic risk. This creates a severe regulatory paradox. You cannot subpoena an artificial neural network with billions of parameters to ask why it crashed the market. You must install a leash before it acts. The architectural safeguard designed for this is the Hybrid Deep Learning Framework. This visualization shows the mathematical leash, nonlinear stochastic differential equations, or SDEs. These possess unyielding, rigid boundaries of probability. The hybrid framework forces the AI's intuitive commands through this rigid math engine before they reach the open market. If the agentic AI hallucinates a panic and demands a massive sell-off, the SDE calculates that the trade violates fundamental statistical bounds and immediately blocks the execution. Because these SDE limits are calculated using traditional calculus, every blocked execution and constrained probability remains perfectly verifiable and audit-ready for Basel III regulators. Wall Street secures its survival through a deliberate contradiction. It relies on the oldest, most rigorous forms of calculus to tame the wildest, most unpredictable neural networks ever built. The transition from human to machine was inevitable. Standardizing legacy risk code solved the opacity crisis, but it created a data speed trap that made agentic AI an absolute structural requirement. Understanding this transition requires returning to the core philosophy anchoring Mahanta's entire infrastructure. Model risk is hidden risk. As we enter fully autonomous financial waters, the industry faces an immense question of accountability. Who is responsible when a hyper-complex model inevitably hallucinates a systemic collapse? The immense computational power that allows an autonomous agent to process global data in milliseconds is the exact mechanism that gives it the power to create economic facts by design. The financial sector is actively pitting the limitless capability of machine learning to scale intelligence against the absolute necessity of mathematical boundaries to scale accountability. The integrity of the global economy now depends entirely on a single mandate, ensuring these learning systems never learn how to outsmart their own guardrails.